We're now on example 4 in section 6.4 on logarithmic functions. We're going to talk some more about domain and finding the domain of a function, logarithmic function, from its equation. But first, let's review the domain and range of a logarithmic function. We found that the domain is 0 to infinity, and the range was all real numbers. So they had flipped from what we found for the exponential. Okay, let's find the domain of each function and use interval notation for our answer. So the domain for this is x has to be greater than 0. Another way to say that is x is greater than 0. Would you agree? So this is our argument here. It's not x minus 2 then must be greater than 0. Adding 2 to both sides, x must be greater than 2. And in interval notation, that means open interval at 2 to positive infinity. If this is our interval here for this, then our argument will always be a number that's greater than 0. So if we had 2, this would be 0. If we had 1, this would be -1, which is not in the domain. Okay. In B, we have log base 2 of the absolute value of x minus 1. So let's see what happens if we set x minus 1 greater than 0. Okay, we need that to happen. However, so then what do we get? X greater than 1. But now, couldn't that, because we take the absolute value, couldn't we have x minus 1 also be less than 0? If this is a negative and then we take the absolute value, we're fine. So then x can also be less than 1. But what can x not be then? Because it can be a positive, it can be a negative. That fits in our domain because we'll take the absolute value. Well, it can't be 0. So x cannot, or x minus 1, sorry, that x minus 1 cannot be 0. It can be negative, it can be positive, but it cannot be 0. X minus 1 equals 0, x equals 1. So x cannot be B1, BE1. X cannot be 1. All right, so what we want to say is x can be all positive numbers and all these negative numbers, less than 1, greater than 1. It just can't be 1. So we need to say all real numbers, but not 1, using interval notation. So we'll say you can go from negative infinity all the way to 1, but you can't use 1, so it's open there. Union that with 1 to positive infinity, right? So the only number, that's how we put a hole in the number line. The only number it can't be is the number 1. Okay, now we have x squared. So x squared has to be greater than 0, right? X squared greater than 0. That's what we were just plugging it in here. So for x squared to be greater than 0, x can be greater than 0, right? Any positive number is going to be squared and greater than 0. But x could also be, we're kind of finding a similar situation as here, less than 0, because if I plug in -2 for x, I get +4. So negatives are also fine. So what we find is x cannot be 0. That's the only thing it can't be. We need a hole in the number line at 0. So we'll go from negative infinity to 0, open interval, union that with 0 to infinity, and we have placed a hole in the number line at 0. That's the only number that is not in the domain for this function. Okay, and finally, we have, this is our argument, 9 over x plus 5. So 9 over x plus 5 has to be greater than 0, right? But 9 is already greater than 0. So we don't have to force the 9 to be a positive number. It is. The only way this whole thing would be negative is if the denominator was negative. So we know that x plus 5 has to be greater than 0. As long as this is a positive number and it's not 0, it's greater than 0, then this whole thing will meet our requirement for the domain. Subtract 5, and we find that x has to be numbers that are greater than negative 5. So let's just test some. Negative 4 is greater than negative 5. If I put in negative 4, I get 9 over 1. That's perfectly fine, right? So this does it. So we want to go from negative 5, but don't include it, open interval, to positive infinity. All right, let's summarize these properties of the logarithmic function. Again, we're just kind of revisiting this. The domain is all positive numbers, all positive real numbers, 0 to infinity. The range is all real numbers. The x-intercept is 1, 0, and there is no y-intercept. The y-axis, x equals 0, is a vertical asymptote of the graph. Okay, we didn't investigate this, but we did find that the function was increasing. In our example, a was 2, when a was greater than 1, and it is decreasing if we have an a between 0 and 1. And we'll see that down here. The graph of f contains the points a1, 1, 0, and 1 over a, negative 1. The graph is smooth and continuous. With no corners or gaps. Okay, let's investigate. Let's first look at the one that was like what we just did, where a was 2. This is what we graphed the function, the exponential, and its inverse on the same graph. We saw that it reflected over the line y equals x. So notice the points on our log function, 1 over a, negative 1, 1, 0, a1, that we listed here. It is an increasing function. We have a vertical asymptote, right? It's smooth and continuous, no corners or gaps. Now, we did not graph this one, but let's look at it. We're given the exponential that we saw in section 6.3. When we have an a that was, I think we did 1/2, a was 1/2. Then, if we reflect this one over the same line, y equals x, notice what we get, the log function here. Okay, so it is a decreasing function. As x is getting bigger, our log function is, our y values are decreasing. But all the other things still hold as far as asymptotes and domain and range and points on the graph. Okay. We'll also look here now at the natural log. And the natural log comes from that base of e. We already looked at the exponential. We had a page where we looked at when the growth factor was e. So we looked at that in an exponential form, but we need to look at it also as its inverse, the log. And ln x means this. If you have log to the base e, if you have log base e, we have a special way to write that. We don't write log base e, we write ln, because that refers to the natural log, because as I said, this occurs a lot in nature, the base of e. So in other words, y equals the natural log of x if and only if x equals e to the y. So you see visibly it looks just like what we did when we had a base of 2. It physically looks very similar. But what we're getting from this is now we don't call it the log base e. So if you look back, we had in example 1c, we had written that we had x equals log base e of 10. So I want you to go back to that example and now make this final statement that we would then correct that and put natural log ln 10. It has no subscript because when you see ln, it's implied that it is e, the natural log. So this is back at example 1, part C. Go back and make that change. We didn't say it there because I wanted to wait till we had gotten to this page, but now we'll make that note. This is not how we would write a log with base e. This is how we write it. And you will see this on your calculator. You have natural log. It's on the same key as your e to the x. You should see ln, and that's the natural log. We also have something called the common log, and this is the other one on your calculator. It's log base 10, and the way we write that is with no subscript. When you just see log with no subscript, it's implied that it's base 10. So again, the graph looks similar to everything else we've done, but we're just exploring here the understanding that when you have x equals 10 to the y as your where 10 is the base, we write it just as log with no subscript. And you have that key on your calculator also.